editing to do.
All right, very good. All right, so Dr. Parsai let me know recently that we purchased a new piece of equipment for the clinic, so I figured I'd do a little looking into it. And so today I'll be talking about the TREF chamber for small field dosimetry. So in general, I'll be talking about some concerns with small field dosimetry, just a little refresher about things we already know about the problems with making these types of measurements. Then I'll get into more of the nitty-gritty, just some specifications, some interesting fast facts on this TREF chamber. Then I'll compare some different small field dosimetry inquiries. So this Cheska article is more or less like an expanded version of a technical note, a more formal write-up from when they really initially started to market this product in 2016. And just very briefly mentioned this last article in medical physics, detector response to the buildup region, small MV fields. In this inquiry, they made use of a PTW TREF chamber. So just a quick kind of highlight of what people are using it for without getting into too much depth of that one, because they look at a whole range of detectors and their performance in the low dose region, and really I'm just interested in the reference chamber they were using and how accurate they deemed it to be. So some challenges for medical physicists in small field dosimetry. So field size ranges in radiation therapy, you could have anything from these magna fields, that would be something on the order of what you'd use for whole body irradiation. Traditional fields, things we're used to going up to 40 by 40 with the true beam. And then once we start getting below 5 by 5 down to 4 by 4, we really start thinking about daisy chaining with a smaller detector to do any of our dosimetry measurements. So the small field range between like a 0.3 by 0.3 and a 0.4 by 4 field, that's when you would consider using this PTW TREF chamber. So challenges with small fields. So we have this lack of charged particle equilibrium. It's going to be dependent on the secondary electron range and the photon energy. We have collimator obstructing the source from the view of the chamber. I have an image that's pretty useful for demonstrating this effect later on. And basically once your detector starts getting comparable to the field size, you really are kind of limited in what you can actually measure for that field. So just in terms of considering charged particle equilibrium from this electron range, it's roughly Dmax in the forward direction, and in the lateral direction, there's this sort of equation here that I got from an AAPM summer school presentation, but it's nearly energy independent and usually somewhere between 8 and 10 millimeters, roughly the same as you would imagine the penumbra for your beam being. So for charged particle equilibrium, you're going to need a lateral range of roughly 16 to 20 millimeters. So once you start getting down to these levels, these are very small fields. This source occlusion is pretty easy to visualize from this image on the left here. So the source will be sending out radiation kind of diverging from it, and once your collimators and jaws get tight enough in, it will partially occlude the source from the viewpoint of your detector. So you end up getting these profiles that we see on the right-hand side of the screen. So once you start getting past this sort of critical point of the occlusion of the source from the view of the detector, you start to get inaccurate full width half max of the profile to the point where it even gets a little bit wider than the actual field size setting, looking at figure C on the right here. And so just important to keep in mind some of these problems, but part of the interest and intrigue into these sort of small field measurements really started when we, as a field, were looking more into making these stereotactic treatments possible. We're started to be able to see these smaller lesions and starting to get the mechanical side down to where we could treat them somewhat more accurately. We needed dosimetry that could back that up. So in Das's article here, it was more of a literature summary and just kind of highlighting the need for like a unified approach towards the small field dosimetry. That's this article compared a variety of detectors to Monte Carlo predictions. So they have everything from 0.015 to 0.125 cc ion chambers, parallel plate chambers, films, TLDs, diamond detectors, everything they could find data for at the time. And this really spurred the movement towards a review of small field dosimetry. Somewhat famously, although this is an older article, we have with cone diameter decreasing, we really get these cone factors varying wildly from different studies across different institutions, ranging anywhere of 12%. And again, these people are more or less working with the same machines. Each one's not going to be identical, but you'd expect maybe deviations of 1% or 2 between like a true beam nowadays. Whereas, sure, they might have been using Clinax as well. This is 2000, but to have a 12% range, and especially diverging in the small cone size, it really is kind of apparent how important good small field dosimetry is. Across different detectors, Das highlighted that you could expect anywhere of like 14% of range for people at the time. Again, just sort of contextualizing this push into really making these measurements as accurate as possible. So getting into one particular aspect of making these measurements accurate and precise is using this PTW TREF chamber. So specifically, the TREF chamber is used for reference measurements. Is that out of the way? So it's necessary to adjust measurements for small deviations, small variations in output when scanning. This is useful for PDDs or any sort of profiles you'd want to do. But you start to run into this problem, how you actually want to measure it. So if you put a thimble chamber in the corner of the field for a larger field, it really isn't as much of an effect. But now you're starting to block a pretty significant portion of these smaller fields that are only a few cm across. And so you start to limit yourself in terms of, okay, well, am I really seeing the like true output if I'm kind of messing with this whole corner of my field? Am I forgot the other point I was going to say. Either way, the chamber mounted at depth in the water tank is another technique. So basically going past the point you want to be measuring at and trying to measure more or less exit dose at the bottom of your water tank is another approach people adopted. But recently, PTW's TREF chamber, which stands for Transmission Reference Chamber, and an IBA, I believe it was Stealth Chamber, is what they called it. Basically, these chambers are designed to span across the entirety of the field you'd be measuring and be very minimally attenuating. So this is the sort of newer approach, these large flat ion chambers that you just send your whole beam through and try to perturb as little as possible and compensate for the fact that it's very kind of thin by the fact that you're really not perturbing the beam much. And so I'll kind of be outlining how the IBA stealth chamber and PTW TREF chamber, both very similar, kind of try to tackle this issue of your reference measurement for small field dosimetry. So I'll move again. So up in the corner here, we have our TREF chamber. So again, your beam is just going to shine through this down in the water tank. It's a small parallel plate transmission chamber. I don't really know why they call it small. It is going to go across your whole field, but it's designed for small field dosimetry. So it's a vented chamber for use in relative dosimetry for high energy photons. It has a high nominal response. It has 10.5 cc's of volume in there, so it is a pretty large chamber in that respect. And they claim no measurable perturbation of the beam. They do measure the perturbation, but it is all less than 1%. We'll get to that later. So really small attenuation. You can mount at pretty much any position as long as it's at least 20 cm from the surface of the water. So anywhere from 20 centimeters up, it's all the same. So you really don't have to be too concerned with your setup for this thing. Just more or less get it in the right spot. You know it's not right next to the surface of the water, because then you start to run into this issue of having like backscatter from the tank itself really being like significantly measurable in the reference chamber. But and it's not influenced by vibrations that could be caused by your scanning motors as they're sort of running. You can see the ripples in the surface of the water, but it really doesn't seem to bother the reference chamber very much. So again, this is just a illustration of the general scheme here. So your field is going to be coming in, passing through the center of the TREF chamber, and then you'll be making your measurement down here with whatever field detector you choose to use for your study or your data for your LINAC. So the polarity effect for this chamber is quoted by PTW to be less than 1%. Leakage current is less than 100 femtoamps. Water equivalent window thickness of 2.06 millimeters for photons. Transmission was greater than 99% for all energies over 6 MV. Just kind of emphasizing that, yep, the polarity effect's low, like you'd expect in a good ion chamber, very minimally attenuating, like you would want if you're going to be placing this in your field before you make measurements. And you can really measure some crazy dose rates with this thing. You're not quite getting to like a flash dose rate, but you have greater than 99.5% saturation at 21 gray per second. So these are pretty crazy dose rates in terms of what is more standard in radiation therapy recently, but you're not going to get anything near like flash dose rate, which I don't know, like 100 gray per second or something like that. So again, just taking some insight here from a PTW technical note. They examined their chamber in similar circumstances to the IBA chamber is what they were trying to do like an apples to apples comparison to. So this is kind of PTW's answer to the stealth chamber. So they're like, all right, we'll do a similar thing to you guys. We'll set up to like our minimum recommended distance from the water surface and just verify that our measurements are still accurate. We're not really attenuating beam or measuring something we wouldn't expect to be. They were using the largest field size and the highest energies that they would recommend using for the chamber, and they measured PDDs and profiles. Now, here we have a PDD scan with the microdiamond detector. The measured PDD with the TREF chamber is in red, and there is a PDD without the TREF chamber, dots connected by green lines. You can't even see the green line because they just lie right over one atop another. So they're using an 18 MV clinic here, 5x5 field, and the detector to surface distance of 20 centimeters. And they're showing the gamma analysis at the bottom here, 1% dose difference in 1 millimeter DTA. So again, really tight criteria. At pretty much any point you're measuring is going to be below 1. Then they repeated the same to compare 2 PDDs recorded without the TREF chamber, otherwise conditions being the same. Again, your gamma is kind of hovering right around, 0.2 plus or minus 0.2 for the most part. But the takeaway they want us to learn here is that the TREF chamber does not attenuate the PDD curve. Any instability in the measurement is just due to quantum noise of the measurement itself. So with and without this TREF chamber in place, it's all more or less quantum noise you're going to be seeing in your gamma analysis for the PDDs you measured, which is a good thing if you're going to be using this to block across your entire field. So here, beam profiles using the TREF chamber. So green data used the TREF chamber while the red did not. So again, you can see a very slight separation kind of near the center of the field off to the right side. But the gamma value, again, was on the same order of magnitude as just what they would expect for quantum noise alone. So with these tight 1%, 1 millimeter criteria, they're still measuring exactly what they would expect with or without this chamber in place. So another interesting bit here, so measured for 6 MV and 18 MV beams at 5 cm depth and 100 centimeter SSD, pretty standard setup for the most part, a geometry that's pretty easy to understand and useful for comparison. So Here, they're just telling us the transmission between several different measurement chambers they placed at that position, and then had the TRF chamber in the field or not in the field. And again, even for the 6 MV field, it's less than 1% attenuated. 18 MV field, it's a little over 0.5% attenuated. This isn't going to perturb your beam to any great extent. So just a couple more data points to show that the TRF chamber really is just kind of like a window you're shining the radiation through rather than anything else dramatic, and you still get your sort of reference data. So here's the TRF chamber in some relevant literature. Here I'll talk about Cheska's 2016 article examining some of the other aspects of using a TRF chamber. So Cheska just kind of outlines, you know, the maximum square field size we would want to use for different geometries based on where you're mounting the chamber. Any sort of perturbations that Cheska measured, as well as the comparison with other reference signal methods. So we'll just get right into it. Maximum square field size. You can, for the detector to surface distance, really this 20 centimeters is about as close to the surface as the manufacturer would recommend using. But the resulting length of the square field in millimeters, you can get a reasonable size field measured with this chamber, 72 millimeters square. But obviously, if you start mounting up closer to the head of the linac, you can start to use a little bit larger fields. But really, you're kind of comfortably past the point where you would want to start daisy chaining traditionally anyway. Because once you start getting down about four by four field is where small field dosimetry really starts. So you're able to get well above this value pretty much no matter where you mount the device. So a useful feature. Again, sorry for the kind of fuzzy resolution. They were this way in the paper itself. But anyway, we have in-plane profiles for a 4x4 field. So with mounting the reference chamber at 20, 10, and 6 cm away from the tank, you're really not seeing too much variation at all. And again, this is going closer than the manufacturer recommends. Again, PDDs measured with the TREF at 20, 22, and 24 cm. So this is kind of starting to be in the range where they recommend to start using it like 20 and further away from the 20 cm and further away from the tank. So really not too much to say other than the fact that the positioning of the TREF chamber is not going to mess up your measurement. So even if you had to tear down and then set up on a different day to continue measurements and your setup were slightly different, you wouldn't see the difference from the TREF chamber's positioning itself. So really the only thing you can see is when mounted really close to the water surface, like starting to be in this closer region than recommended, you do see some variations in the buildup region of the fields themselves. So this is really zoomed in. So this is the stuff, if you're looking very particularly at this buildup region, you want to be careful where you're mounting your TREF chamber, and in particular, just not being as close to the surface as some of the data points in this slide would indicate. Because once you start getting up to 18, 20, 22, 24, they're all sort of bunched up at the bottom. But this 8 cm and 11 cm detector surface distance are the ones where you have that variation. So that's kind of where that manufacturer recommendation is coming from. You can't just put it anywhere, but really it doesn't have a drastic effect even if you did. So this I thought was pretty interesting. This is comparing a reference measurement with the TREF chamber to a reference measurement with a 0.125 cc ion chamber in the field. So left we have the TREF chamber, the reference measurement being in red, whereas the reference measurement from the standard ion chamber in the field is on the right. And you can just see, just looking at the red lines themselves, a lot less noise when you're using the TREF chamber. So this thing is going to be really stable and not going to add too much more noise to your measurement. So you're going to be getting as close, as accurate values as possible when using this thing. So in this article, there's a quantification of the TREF's effect in the buildup region. This is just a very brief mention of this other study. Again, they were looking at a lot of chambers to determine what's the most accurate way to measure in the buildup region. And their reference chamber they were using for this study was a TREF chamber. So I'm just focusing on their small little assessment of how good the TREF chamber is. So the quantification of the effect was a minor focus of the paper, but still important to Wegner's findings. So the TREF chamber was mounted pretty high. This is a 47.5 cm from the water surface, so this is a lot further up, closer to the head of the Linac. Wegner says that the measurements were exemplary. They were really happy with, being able to use this TREF chamber. So they made measurements with and without the TREF chamber onto an unshielded diode remaining in the field to sort of quantify the effects of the TREF chamber for their study. And so they said their results in the buildup region were accurate to within 1%. So 1% was the deviation they the max deviation they were able to measure when introducing this TREF chamber versus when it was not there. So that's kind of where they quoted the largest amount of uncertainty in their measurements. So down to 1%, again, what we'd expect from the technical specifications given by the manufacturer. There's also this brief note on buildup region electron contamination, several percent with most detectors accurate to within 1%. So this is just kind of a frame of reference when they're introducing a small lead field, a small lead foil into the field to try to quantify electron contamination for their machine. Their TREF chamber was like a third of the electron contamination in the beam for when you're measuring in the buildup region. So just kind of a frame of reference. The perturbation from a TREF chamber is much less than your electron contamination would be if you were measuring a PDD with and without that lead foil. So in conclusion, small field dosimetry has a number of issues, a lot of aspects that are not necessarily addressed by the presence of the TREF chamber, but we start to run into these charge particle equilibrium issues, these source occlusion issues, and reference chamber placement in particular is what this product attempts to address. And so in using this TREF chamber, we'll have this minimal attenuation of the beam, lower noise than alternative methods, the chamber distance from water acceptable within a wide range. Like setup isn't super important. You're not really going to ruin your whole measurement by doing this. And since it's been out for a little while, it's been well characterized by the manufacturer and the initial investigators. And then it's gotten to the point where people are actually applying this in studies that are working on other aspects of small field dosimetry, just kind of showing that it's gaining some amount of trust out there for being used. So, and there are my references. So.
Can I question? Yeah. I didn't understand what was the field size of for each of these measurements when you put the chamber, what was the field size there?
Okay, yeah, let me go back a little bit. So are you saying for these measurements here?
Yeah, for each of these paper that you provided the picture.
Okay, yeah, so for this, it was a 5x5 field, and the detector was 20 cm from the surface of the tank. I think everything in the technical note from PTW is for a 5x5 field, and yeah, I believe these, 5 cm depth, 100 SSD, I believe 5x5 still. For this follow-up article, like they were looking like a 4x4, so around where we'd start considering small field dosimetry. And then in the last paper, I don't remember off the top of my head what field sizes when they're used. So I'd have to look at that, but they were specifically looking at the buildup region and small field dosimetry. So something comparable, I imagine. I'm not sure what range off the top of my head.
So here is the water tank. So they put the chamber above the.
Yeah, and the air above the water, just like we would.
So the field size that they define is under.
Oh, it's at 100 still, so it's much smaller when it's going through the reference chamber. Yeah, that's why we kind of get this table here of resulting square field lengths. This is like at 100 from the source to surface, kind of like we'd standardly define. But I think in one of the papers, I can pull it up, they give the actual dimensions of the PTW chamber. I think it's like a 4 cm radius, something like that.
The total you said is, the volume was 10?
10.5 cc's, and then I think the radius of the chamber was around 4 cm.
So I have a couple of questions for you. Well, actually, anybody really in the audience, but does anyone think that the design of this chamber looks familiar in some way?
Monitor chamber.
Yeah.
Yeah. Yeah, I mean, basically, it looks like a monitor chamber, right? And it acts like a monitor chamber as well. It's just a monitor chamber with a BNC connection, a Tri-X connection on it. And also, like, it looks like it might have a more substantial casing, because you could definitely put your finger through a monitor chamber, but I doubt that a monitor chamber even attenuates the beam by 1% for 6X. I bet it's even less than that, because it's basically just a tiny little thin drum skin, but it would also not be very durable. It probably wouldn't last very long out in the open like this chamber. The next question I have is, does anyone know of an alternative to this? So let's say you were designing an ion chamber specifically for this problem, small field dosimetry. You want to make a reference chamber, but you know you can't just stick a normal reference chamber in the field because the field's too small. What's an alternative to this? Because there are actually other ion chambers on the market that do the same job, but in a different way, different design.
Like Ed said, there's a strategy of just going beyond the depth that you were measuring at, and as the beam continues to go away, you've got the inverse square law playing to your benefit for once, and the field size gets larger. You can just stuff it in the corner down there past your measurement to get your reference values.
That might work for square fields. I don't know how good that would work for cones, unless of course you've got a very, very deep tank, very deep, like to the point where you're inverse. You know, you've got 1/r². The beam's diverging, so it's getting big enough. So that might work, but there's an alternative strategy that's kind of like this, but a bit different. It's a different design of chamber altogether than anything you've maybe seen.
Are they like ring shaped? No.
So what the alternative for this is, you take a very large volume ion chamber, maybe about 300 cc's, 300 cc ion chamber, and you put it on the side of the machine so that it actually picks up the background radiation, scattered radiation from the head of the machine that's created when the beam is on. So the idea is that if there's any fluctuations in the output of your beam, this ion chamber, which isn't directly in the beam, but is close enough to the beam and has a large enough volume that it's sensitive enough, could actually pick up fluctuations in the output of the beam. So you're not shooting through it at all. It's just a big ion chamber next to the beam. So I think Sun Nuclear might sell this. Theoretically, it might even be it could even be a diode array to be even more sensitive. But you slap it on the side of your machine. Theoretically, you do it underneath the covers of the machine. So it's actually under the plastic covers, but stuck to the shielding, the head shielding. And it's actually measuring the beam indirectly through head scatter. I haven't seen any papers on it, but I've heard that is an alternative to having a shoot-through ion chamber. So if you ever come across that one, that's because I've never seen this chamber before. That was actually the only one I'd ever heard of for this application. All right, my final question then is, do you think there's any benefit to measuring output factors with this ion chamber? Because at the beginning we showed data of how difficult it is to measure an ion chamber. So how difficult it is to measure output factors for small field dosimetry. That was kind of like Das's conclusion, is that the small field dosimetry readings are all over the place when it comes to output factors. So the question is, would this help?
I think it could. Really, if you're getting down into why there's this kind of user to user variation, like my instinct is to say part of that is setup. Part of this is people are like blocking too much of their field with their reference chamber, or potentially blocking like the beam's eye view of the like actual field chamber you want to measurement. Like I'm trying to think how else they'd have like a 14% variation if there weren't some sort of issue with like properly mounting of reference chambers. But again, like that's only part of it. I'm sure there are other aspects. Output factor specifically, I don't think it's the most useful application of this chamber. Like I think you really stand to benefit if you wanted to measure beam profiles for something more. Or maybe even PDDs where you're getting up towards the surface where you really even have less room to place a small like reference chamber. But I think it could help.
Anybody else got any thoughts? Any other thoughts?
I mean, if you're doing an output factor, you don't really care if your machine's dose rate changes throughout it, because you're just looking at the number of MU.
Yeah, so I would think it would be a bit sketchy to do these measurements with a reference chamber. I don't really think you're going to get much value because I don't think you need to do you don't need this reference chamber. Yeah, certainly. To Ed's point, if you are putting a reference chamber and you're putting it in the field, you're probably screwing up the measurement. But the real point is, why would you put a reference chamber in the field? You're going to shoot 50 monitor units, 100 monitor units. You're going to do the measurement 3 to 5 times. If there was a measurement that had a fluctuation in it, if it was a dose rate fluctuation, you probably don't care. The machine would just shoot more or less length of time until it balanced out. It wouldn't affect your readings. Whereas if you're scanning, it does. If you're scanning, you see fluctuations in your profiles. But for output factors, you don't care. So you probably shouldn't be using this for output factors. But on the other hand, if you did, I don't really think it would necessarily make much of a difference. That attenuation should cancel out. You just wouldn't necessarily, it's not going to fix the problem. The main problem with doing small field dosimetry of output factors is just simply detector variation, machine variation, and the extreme difficulty of having an ion chamber or whatever it is you decide to use exactly positioned in the center of the radiation field. It's very difficult to do it. And choice of chamber is so critical. If you use what you're thinking is appropriate micro chamber, but you go down to like a 4mm cone, chances are you're screwing it up pretty bad, and your output factors could be way off. And that has happened. People have like commissioned stereotactic cone systems and used the best stereotactic chamber they could find, and they've still screwed it up because you just cannot measure a 4mm cone with any reasonable dosimeter. Like, it has to be something crazy. I don't think we have anything that could do it, really.
If you wanted to measure outputs for a 4mm cone, could you start to play games? I mean, even if you like put it further away from the machine and try to play some game of like an inverse squared correction or something, I still don't think you would gain enough in size of the field, I guess.
Yeah, I mean,
Are films
maybe
suitable?
W1 could theoretically do it if you mounted it perpendicular, but then you have to have a chamber caliber. You have to have some sort of correction factor for the W1. If you really read many papers on small field dosimetry, one of the things you start to notice is that it's machine specific. So I think that's got something to do with the way the electron beam is focused onto the target. For most measurements, that makes very little difference, but for small field dosimetry, like very small variations in the position of the beam on the target could actually have noticeable differences in the output factors for very tiny fields, partly because of that occlusion that you talked about.
Yeah, there's an AAPM summer school presentation that goes into a lot of aspects of small field dosimetry from like 2014, I think.
Yeah.
And they highlighted a source just to what you were talking about. Actually, they had like source sizes for different linacs of like the same model, and you could actually see like their dimensions, and they were like pretty different in terms of shape and overall size too.
Yeah, I'm not an expert on small field dosimetry, but from what I've seen, people bring up new problems all the time, and it's like, yeah, small field dosimetry is really difficult because of this, and this. And I don't know if anyone's solved all those problems. There's like I think it's an ICIU report that came out. Is it ICIU? So there was one on small field dosimetry, and they used a reference chamber. I'm sorry, not a reference chamber. They used a W1, and they said that should be the gold standard, or they used it as a gold standard, and that's not even universally accepted that it should be the gold standard because of the inherent correction factors that need to be applied to a scintillator. Yeah, so there's stuff that's come out since 2014 that's just added to the. Oh yeah, this one. I remember that.
Yeah, so like some of these are like crazy how different in shape they actually are.
This is a sim.
All right. Who wants this one?
Yeah.
So hopefully the true beam is the one in the middle,
Yeah.
or maybe one of the ones in the middle, and maybe
Yeah,
one of the terrible ones is like a clinic or something.
I think from what I remember, aren't most of these clinics, or most of these like
This is a 1993 paper, so I think these are all going to be like the clinic platform, if I had to imagine.
I nowadays resource size is not important anymore, isn't it? I have seen in papers they mention.
It might
For
be
small
back in-
field dosimetry, you're saying it's like so close of a range that it doesn't make it. Oh,
That's what I saw.
yeah, I'm not sure. I didn't see anything on that yet. But yeah. Oh, here's some tutorials. pretty reasonably similar, so that's good.
I think those are much smaller than the ones above, right? What were the units on those?
I don't think it did
This
anything.
doesn't really give you, it's not labeled well. I think it was just a general, like, a comparison for saying like, oh, the same machine doesn't give you the same spot size.
Okay,
And then this is, I think, just one variant you're getting.
that looks like 3 of them probably.
Three
Three
rooms.
rooms.
Oh yeah, three rooms there. So if you get small,
Consistent.
probably smaller than 1 by 1, you may still see it, but it may not be as bad as it was before. Like, I believe that.
This is kind of what I would expect. When I was doing Monte Carlo simulations, the spot size of the electron beam hitting the target was 1 millimeter. And so that would mean that our source of photons is 1 millimeter in diameter. And that's kind of what these are all showing. All the numbers down in the left along the right side suggest that it's like a 1 millimeter by 1 millimeter source. So what they were calling source occlusion, you wouldn't really think that would happen at all, right? In a true beam, because if your source is 1 millimeter, unless you use a 1 millimeter cone, like how would you get which we don't have a 1 millimeter cone, how would you get any occlusion of the source? I mean, you could maybe get some tiny partial occlusion, but like, I don't even know how that's, maybe that source occlusion thing refers to some older machines, and maybe it's not an issue with true beams. Doesn't look like it should be. The source is only 1 millimeter.
I guess I just have to know how they're measuring this, though.
Inverse squared too.
Yeah.
So that's 1 millimeter is probably more like 2. That's right.
Yeah. Do you know how they make these sorts of measurements? Like, I mean, just in the slideshow, it doesn't give enough information. But if this is measured like on a film at the target, I'm surprised they didn't burn through the film completely. But like, I don't know if this is like effective source size at 100 like centimeters or what?
No, this is probably right on the target.
Right on the target.
Yeah, it should be measured at target.
Okay, so yeah, it's pretty good then.
But I guess you make a good point. I guess there is, the source does have it would appear larger, right?
Yeah. I mean, what's the distance from JAWS to the target? 40 cm? Is it not even? It's not even that, is it?
I thought it was around 30, 40.
30.
Sounds right.
Yeah, something like that. Primary collimate is about 10 centimeters. Got to somehow squeeze in your flattening filters, your primary collimator, carousel, and your reference chamber. Your monitor chamber. Which, if you want to go down another interesting rabbit hole, there's a topic of research that was done on the effect of the jaw position on the output of your machine. Because when the jaws are closed to small field sizes, the jaw actually sits very close. The top of the jaw, the metal surface that blocks the beam, actually sits very close to the monitor chamber. So you actually get backscatter hitting the jaws and going up through the ion chamber. So in other words, it's counting more dose because radiation is bouncing off the top of the jaws. So it has an effect on the output factors of the machine.
Do you think we're moving to a day then where we need like 2 separate MU calibrations for the machine, like one for large field and one for smaller fields?
It would just be easier to change the output back. Just no.
Just change the output and change it on the output factor side?
Yeah. Right.
Well,
I mean, it's kind of academic, yeah. I mean, if as long as as long as the problem is consistent,
Yeah.
it kind of cancels itself out.
I think in trying to fix that, I would just come up with a way to confuse a lot of people, like the lead foil did with TG51, and then everyone's machine would be different.
All right, well, cool. I gotta let you guys get off and do whatever it is you need to do. I'm gonna hit the road.
Alrighty.
Alrighty. Have a good weekend.
Yeah, have a good weekend, everyone.
Take it
Yes.
easy.
See you later.
We're also getting a micro diamond.
Oh,
I didn't talk about that then.
Yeah, we were getting.